So, what am I going to talk about today? There'll be a brief review, well, it may be a coverage of Comonads if you haven't come across them before, just to get the intuition across. That'll be followed by a bit of a discussion of Freemonads. I'll introduce the motivating example, which is a little toy that'll carry on through the talk. And then I'll get to the Cofree Comonads, which is what you're here for. And I'll show you how to use them, how to clean them up with Comonad transformers, and then how to make free and Cofree work together for awesomeness. So there's a non-goal to this talk and a couple of goals. I know you all love your category theory, but we're not going to go into a deep dive. It's more about the practical usage of these things. So I'm aiming to get the intuition across, and I'm also hoping to get the inspiration across. I have a lot of enthusiasm here. There'll be things at the end I'm talking about which aren't quite ready but are awesome, and I want you all to collaborate with me, or at least ping me to make sure that I'm writing my follow-on blog posts. But the talk itself should have enough gold to keep you happy, I hope. So when talking about monads and comonads and how they work together, a good starting point is to think about folding and unfolding of lists. You fold the list down to a value, you unfold starting at a seed value, and you build up. So a monad is, you build up from pure values to some computational context. It's like an unfold. Whereas a comonad, you have some environment, and you're bringing it down to a pure value. And combining the two can have good results. So to get a little bit more concrete about that, we'll have a brief look at comonads using Haskell syntax. So a comonad is the categorical dual of a monad, which is why the M gets flipped to a W, apparently, from the same people that brought you row and lambda for right and left. In a monad, we use return to kind of go from a pure value to build up our context. In a comonad, extract is the dual, which takes our environment and pulls a pure value out of it. Bind, you can think of as we're building up our context in stages. We're partway there with M of A. We have our ability to take our pure value and build up to an M of B, and we bolt them together. Extend is co-bind. We're on our way to a summary. We have a W of A. We know how to step it down to a B, and so we step our whole context down to a W of B. Monads have join, which peel off a layer. Comonads have duplicate, which add a layer. All very abstract, not super useful for you at the moment. The best way to get the intuition across, I find, is with a list zipper. This is the data type. It has the focused element in the middle. It has some lists for context on either side. The list on the left is reversed. This means that we can efficiently move left and right through the zipper to change the focus, just because of the way lists are defined. If we print it out, we can see the focus for this show instance has special prominence. Extract just pulls out the focus. That's, duplicate gives us a zipper of zipper events. We still have the same main focus here on the third element, but each of the elements is focused on their particular position in the copy. Sometimes that's really useful. Here, it's just line noise. Extend is where it's at for getting the intuition across. So we have some data. Pretend it's from a list zipper. We'll call it Z, the zipper. So if we define the latch function, which takes the maximum value given a particular zipper from everything to the left, including the focus, then extend latch is going to apply that at every focus, find that summary value, and then put it into position. So it gives us our new function of the maximum we've seen to the left everywhere. So it takes a context, gives us a value, and applies it everywhere in that context. So it's we're making that function do a bit of work. Peak, we can look for all of the elements which are larger than the elements immediately on either side of them, and we can just, we're defining it for one point and we're getting it everywhere. We can do this for windowed moving average as well. Take samples from either side, average them, do that everywhere. And we can compose these. Here are the peaks of the windowed moving average. Gives you a little bit of a taste of the intuition behind Comonads. It's all you need for this talk. You can find plenty more online, and I'll be posting links and all kinds of stuff, or come talk to me. The next piece of the puzzle is the Freemonad. Conrad talked about it in his talk, but I'll go through it so I can weave my example through. The data type looks like this. If f in this case is a functor, then free of f is a monad for free, as in beer. The free consists of either a pure value or a functor full of other free values. So it's a tree where your functor is your kind of branching factor. So our underlying functor for our example is called adderf. It represents a toy little service that you probably don't really need. We can add a value to a total served on some server somewhere, and we can get told whether we've overflowed that counter. K, the type parameter, is what we're doing next. Whether or not we overflow we can choose what we're doing afterwards. We can clear the total and then do something else, or we can ask for the total and then use the total to determine, what's going on after that. We need it to be a functor to use it for this trick. Just use derived functor. It's trivial. But to show there's no cards up my sleeve, I'll just put this up here to publicly commit to the fact that this type checks. And then using this definition again, we can define adder as free of adderf. If we unfold this a little, we can see that our adder is either a pure value or it's one of these kind of commands in the DSL that we've written, followed by more commands. It's a big tree of our adder commands. For a usage of this, we're going to build some combinators. The free package on Hackage has liftf. It allows us to translate our data type into a series of functions that we can use to manipulate things in the adder monad. So we can just call add, clear, and total. We can use our do notation. We can traverse collections of these things. And a good thing that we can do with this, or a good example of using this, is that we can find the limit. We didn't expose this as part of our API, but it's kind of implied. We can add until the overflow ticks over, and then we know what it is. So to be good citizens, we'll take the old count using total, and we'll clear it. We'll call out to a helper function, and because we've built our own little monad with our couple of lines, we'll use a monad transformer to actually count out what the limit is. And then we restore the old count and return the result. So this gives us an int in the adder monad. A little helper is in state over adder. We just add 1 to the total. That's our add in our adder. Check for overflow. If there's no overflow, we add to our state counter, and we continue. And when this finishes, because the overflow's occurred, state will hold our total. So now we have a new little primitive built against our DSL. No mention of the interpreter so far. It's just we've built a DSL, we've extended it. We could keep going. We could build a big library of things that work with adders. We could put it up on Hackage. People could do it. They have independence from the interpreter. It means we can write interpreters for different needs. We can write a pure one for testing. We can write one that goes over the network. We can write all kinds of things, and many people often do. And it's all ad hoc. You've got your pure and free constructors, and people tear them down and do things and recurse. And don't do that, basically, is the point of the talk. But in order not to do that, you need something else. You need Cofree. So Cofree is pretty similar. We had a sum before. We had a pure value or a functor full of frees. Now we have a product. We have a value and then a functor full of cofrees. If f is a functor, then we get a comonad for free, and we can latch on to our bare minimum of intuition of comonads from before and put it to good use. So we'll build a co-adder. I couldn't think of a better name. It needs to be able to handle the 3 cases. So it's a product of our add handler, which takes an int and tells us whether we overflows, and then returns new handlers, our clear handler, and our total handler. We also need this to be a functor. And again, we can derive it, but I'll bravely commit to the type checking, although it's trivial. Yeah, and using this, we can kind of unfold this a little. It's a value followed by the new handlers after you go down each of these trees. But we need to build one that actually does something in the same way that we built our little combinators before. So let's put it to work. We want to make a coadder. We've just used types for our limit and our count. We want to get a coadder out. We're going to use co-iteration, which is kind of like a list unfold. We have a seed value, which is on the right, and we have a function which gets us up to our next stage in our underlying functor. So we'll just call the function next and the initial value start, and start will just be our limit in our count to begin with. Next has to return our functor, so it's a co-iter of f. And co-iteration is just going to start with the start value and then next of start and so on. It lazily builds a big infinite tree that will just keep handling things, and we just have to specify how we get from one level to the next. So we'll be expanding on our next function. We can just handle each of the operations individually here. And that's all we have to do. And they're fairly simple. So to clear the total, we just set it to 0, right? If we want the total in our result, when we ask for it, we just pull it out. Add has a few more steps to it. To add x to the count, we do that to x of prime, and we check for overflow. We have our own internal limit, and we return that. And then if we don't overflow, we're updating the value, so we calculate that as next, and we return that. And now we have an interpreter. It will happily do our adds, clears, and totals. It's completely separate from the client code. We can write library code to expand on this, and with that same independence, which we'll get to shortly. And we can reuse it, and we can write different clients for different needs, and you could tear down the structure and write your own little clients, but don't do that either. So we'll clean this up, and then I'll show you what to do instead. We'll clear it up using comonad transformers, which are just like monad transformers, slightly different. So things flip around, we drop down into a slightly smaller context while we're summarizing, and we make use of it. Not going to get into the theory, the examples should make it fairly clear. So this is what we had. We're going to add in the store and environment comonad transformers to our base. They correspond to state and reader. We're going to flip across to the transformers-based co-iteration. And then we're going to clear our throats a little. So we build up our store and environment comonad transformers. These correspond to run state and run reader from monad transformers. We're doing them at the start rather than at the end because arrows have been flipped and they're W's and not M's. And all we have to do from here is update coadd, coclear, and cototal. Coclear and cototal only use the store or the state. So the state monad, the bits that we're interested in, are the get and set functions. In store, these change. So get for the state monad returns in S in the monadic context, but we're not building up a monadic context. We're tearing down a comonadic context. So we have pos, which pulls that value out, which is pure. Similarly, set can't just update the monadic context in place. So the store equivalent, seek, takes the new kind of stored value and an old context and gives you a new one. But otherwise, pos is get and seek is set. So we should have a fairly good idea on how to update this. So we remind you of our stack. We're only dealing with the top level here, so we don't even need to lower anything. We update our type signature, and we just set the count to 0 when we're clearing. And after we update our type signature, we just get the total. None of this managing of state for us, we've factored that out. Add, however, has got to duck down to access the environment comonad transformer. It has a function, the environment transformer has a function called ask. It's just like reader's equivalent, except similarly, because we're tearing things down rather than building a context up, a pure value pops out the end. So we'll update this in stages. We have our stack. We change our type signature. In this step, we're keeping our old pure code. We just update the next value. And everything will work if we can find our count and our limit from our stack. But we know how to get our count, because that's just pos from the store comonad. And if we lower and then ask, we can pull the limit out from our environment comonad transformer as well. So at this point, we have Comonad transformers helping us factor out those concerns in our interpreter, but we're using explicit lowers. And so that's kind of transformer style, if you're familiar with MTL, which is useful if you're going to have multiple stores in your own stack and you want to refer to them independently. But if you want to travel a little bit wider, you may want MTL style, where you use type class constraints. So I'll change this bit at a time. So we just throw on the constraints. Comonad store is like monad state. Comonad env is like monad reader. We'll update our type signatures. And then the only other thing we have to do is to get rid of the explicit lower. Ask is part of Comonad env, and we're there. So we now have a Comonad transformer-based interpreter. And we can be very proud of ourselves, but it's just kind of sitting there. So let's put it to work. Dan Paponi wrote about this and called it pairing after Bayhack last year. Ed wrote about it years ago. I haven't found a link, but I'm assuming Oleg did it first. So if we have a functor f and a functor g, a pairing of f and g will allow us to take a function from a to b to r, a functor of f of a and functor of g of b, and give us an r. What now? Well, easiest way to explain it is with identity. We just pull the values out, run the function on the value, and now we've paired them together. We can pair more complex things, like the function functor and the tupling functor. Don't worry about too much of the details. A lot of the time we can pair in the other direction. We could work all of that out, or we can cheat. We can halve our work by flipping the function and flipping the functors. We still get the pairing. So what does this give us? This is what it gives us. If we compare two underlying functors, we can pair cofree and free. It's actually pretty simple to work through yourself. Pure gets matched with your head. Everything else gets kicked down the road. And now we have a pairing. The previous divide has been breached. Well, we have a pairing if the underlying functors pair. And this is where the not so surprising result of co-adder is not accidentally like it is, kind of comes out. I've written it in order to make it easy to pair. Add and the add handler pair up like so. Clear has nothing going on, so we can just call the function. And total is made easy by the fact that we have the function functor on one side and the tupling functor on the other. We can use that instance we used before. We could have tupled the int and the bool function there and used the same trick. You can save a lot of work by using your pairing instances. So now our adder monad and cofree and our co-adder comonad can be combined, like this. Give me an interpreter and I will find its limit. Done. The limit will pop out. We've written our little DSL to find the limit. Any interpreter that type checks will give us the limit there. We can test it. If we threw in a particular limit, it should come out on the other side. The type signature also matches that of extend. So if we have an interpreter and we want to build a slightly richer one, in the same way that find limit extended the DSL, this run limit can be used to extend our interpreter. So yeah, we have a nice clean separation. We can make them run against each other in this pure setting. We can do a little bit more. If we have a cofree stack and a free stack, we can kind of interleave the effects and we get something in our monad out the other side. A little bit messier looking, but that's all right. Then we can come up with this beast. We build an adder in the IO monad, so it'll parse input from a user, it'll display its results, and it'll give us a prompt telling us what our options are if we mess up, because I want it to be total there. And now we can just test it. If we run that, we have our pure interpreter, and we have an IO-based thing, and that will just keep reading from your keyboard and adding and telling you the total until you're done. So that's pretty nice as well. And you can add more and more effects and get fancier and fancier. It's nice. We can clean this up some more. So some of you will have come across Coroducts for Freemonads. It was in data types a la carte. Basically, we had our add, clear, and total, and they're pretty independent. So we can break them out. We can just have our add functionality here. They have functor instances, pretty trivial, and they have a pairing. And we can do the same for clear and for total. Now, and we can do it for coadd and co-clear and co-total. Now we can just type alias, the product sum of them, and we have something that's exactly equivalent to our old adder. And the kicker is that we can do the functor products for the co-adder, co-clear, and co-total, and we've recovered our co-adder. So we have our independence of our parts now. We can work on them individually. There's a pairing between these, which means there's a pairing between adder and co-adder just because we paired all of the parts. So we can travel a bit more lightly there as well. Data types a la carte introduced this little symbol here for saying that our big sum of functors contains, add in this case. So we can still have our DSL, but this will work in anything that has add in the sum. So we can mix and match. If we only had add and clear, we can make use of them even though total's not in the type. We could add logging in, and this will still work because it doesn't care as long as add's there. I kind of dodgied up this to provide the same kind of thing on the interpreter side. So you write your little co-iteration functions in your product functor, you bolt them all together and it just works. So you can make your add and your co-ed independently, and your co-worker can work on clear, and then you can bring them together. So let's do some more stuff with this. A lot of this is stuff that I'm still playing with, and this is the bit where come after me and tell me what you want to hear more about, and I'll be chipping away at it and blogging and collaborating, hopefully, if anyone's really keen. Networking is the bit that's kind of fun. So we have our add, so we can build packets for it. So we have our add request and our add response. The int and the bool have been split up. And then we can build this, which is pretty much like from Conrad's talk. We take a request, and then in some monad, we either get an error or a response, and we continue along. We also have the server equivalent that can handle it. There are functors for these. There are pairings for these. The kicker is that there's also pairings between our network communication and our DSL and our interpreter. And this forms a square that commutes. We can locally, purely make our interpreter talk to our DSL, or we can make our DSL talk to our network communications to the server Freemonad and serialize that to bits and send it across. And then we can come down the other leg, and we effectively can pair our free and co-free instances over the wire and track our error, kind of quotient out the errors. This leads to some interesting things for testing. So we can build arbitrary interpreters or DSLs to test the interpreter or the DSL on the other side. We can also simulate a flaky network link. We can do things like test retry semantics or timeout semantics with some of these things. Other things I want to kind of play with here, co-parsers. So you've got your from JSON which parses and build things up. I was playing with distributive for this, but I'm now thinking divisible might be a better bet because Ed's done a lot of work ahead of me. I'm very interested in how to play better with errors with this stuff. And I really want to play with index-free and code-free, where you can put more invariants in your types and preserve, don't send anything if you haven't opened your network connection, and things like this. And I'm really keen to benchmark density just for fun. So co-density can give you a free speed up in certain circumstances with your Freemonad, and density is sitting in Khan extensions on Hackage, just waiting for me to see what the hell it does. So that's it. My claim is that you should at least evaluate or play around with Cofree Comonads to build interpreters for your DSLs and to play with different ways of pairing them so that that's just a separate concern. Links are partially up and more are coming here. Ed's post and Dan Paponi's posts are up there if you want to go through the original bit of the pairing. And yeah, come see me afterwards. Tell me what you want me to kind of work on next or what you want to know more about, and I will build an orderly queue and interpret it. Cool. All right, thanks.